actually this example is from the textbook. And okay, so this will illustrate the use of monitors. Okay, so here you have class Q, right? And usually this structure looks like this template, like generic data type. So you can have Q of any type. So the Q has got field called head, field called tail, and running objects, which is the content. Right. What's a Q? Q is just a word. So basically, you start here. You're having just two functions. You have something called Q or add whatever, and DQ, or maybe in Q and DQ. So in Q, put something inside the Q. DQ, take an object. Yeah. And you have FIFO, it's first in, first out order. So if you in Q something first, it goes out first. First in, first out. So this is how to create the queue. And of course, a queue, you have many objects, many threads that sit in the same queue. So that's why you need monitors to make sure things are correct. So let's see how we're doing this. Here you have a constructor that's called only once to construct the queue. So you decide the capacity, how many objects you have, and you initialize the head and tail zeros. And then, for enqueuing an object inside the queue, you have this thing now, synchronized. So this is the monitor. So synchronized means that this door or this method, if you invoke or you call this method, only one thread can enter at a time, and the others will be blocked. Right? So and you enqueue something, some object of type T, right? So the generic type. And here's just a standard logic if it's full or not. So okay, so if you enter and you find that inside the queue there is no more room for you to insert your object, you just wait. So you go sleep. You freeze yourself and sleep. And yeah, okay. And when you wake up, what would be the semantic of framework? Check it on the again. But I think you have to complete the standard. So I think when you wake up, you enter the method again from the start. I think, but check it. If there's exception, you handle it, and then if okay, if everything is okay. No, yeah. Let's check. But why you have a while? So this should be some. Yeah, sorry, yes. Yeah, okay. Right, not wrong here. So I think what's going to happen here is that when you wake up, right, you wake up and then you see what's the status of the monitor. If the monitor is, no one is inside, I think you wake up and resume from here. Yeah. That's why you have the while, so you keep waiting here. Not waiting, maybe the wait is wrong. So you keep trying. Just check. You recheck the condition again. That's basically. But if you, okay, so you call the wake has to, so you block, this means you sleep, and then when the wake returns, this means that you are inside here, and then you can do your checks. But you have to check your condition again, because maybe what happens is that when someone removes something from the queue and he wakes you up, someone else was faster and got inside and inserted a new item. So when you wake up and go inside the monitor again, you have to check again the condition to make sure it's okay to insert your object. So I think this is the correct semantic here. Sorry for that. So you insert your object, just standard data structure, whatever you put it in the end, the module, whatever. So, well, yeah, what's interesting here, you make this notify. Right, so notify, you notify one. Yeah, one of the sleeping. Just one. So if you just wake up one person. Oh yeah, because if you wake many here, yeah, because this is very simple operation. They're all waiting on the queue to be full. So there's no point of waking them all and only one will succeed and the other will sleep. So it's better to just wake one. And this is the DQ operation. So you want to remove something from the queue. So again, you can wait here, or you have to wait here if the queue is empty. So So if the queue is empty, then equal tail, you wait. And then when it's not empty, you remove your item and notify also if anyone is sleeping anyways. And then you return. So usually this is very much elegant. It's much better than maybe when we talked about locks. Yeah, it's much nicer to program. And in Java, actually, there is no rule about memory. So actually, memory, or the underlying way you implement the Java bytecode, is that you have a relaxed memory consistency, right? So this will be visible again from your side, right? Okay, so relaxed memory consistency means that it's not sequential consistent, right? So actually, the order of operation observed by other threads will be maybe different from what you actually do. So actually, this is the wrong example for something which I'll explain quickly. So you have here something called singleton or whatever object. Sorry, the function called get instance and return singleton object. Right. Okay. So basically, there's some local variable here or field inside this object. It's called instance. So if instance equals null, right? You do here something called synchronized block. So you execute these lines atomically or mutually exclusive. So no one can interrupt you here or enter the same region. And this is like the name of the object that you synchronize, like the lock object. So this means that, okay, so I enter here, no one can enter these lines, and then it's it, right? So, okay, he's checking here. If instance is null, this means that I should create a new one. This is the idea. But then, because maybe by the time I enter the synchronized object, someone else was faster than me. So then I have to check the condition again. Do I still really need to create it again? If yes, then it just creates a new object and assign it to the instance. And then we return the instance. So it seems correct, right? But actually, because memory is not sequential consistency, you can have very funny things that might happen. Right, what can happen? Right, imagine that you have two threads, T0 and T1, and they are both they're trying to get this get instance. Right, so what can happen is that maybe T0 is fast, it goes here, it goes there, and it goes here, and it goes here. And the other one is still outside. It's no problem so far. Right, so now when you do this, instance equal new single. Actually, what happens here actually is two things. Maybe I'll do very clear in my previous example. But what happens here is, number one, you allocate. Maybe this is the low-level implementation. Allocate memory for the object. And number two, you initialize the object. Right? Right. Okay. So you allocate memory, you initialize the object. Yes. And number three, you assign the address of the allocated memory and initialized object to instance. Yes? So you allocate memory, you initialize this memory, and then you pass or you store the pointer to this initialized memory to the instance. Okay, this low-level implementation, is what really happens on the machine. Now, because there is relaxed memory consistency, so actually Java can freely change this order as much as we like. Right? So, what happened here is that maybe T1 would observe that this thing happened first, and this is number 2, and this is number 3. So actually, you don't yet see the effect of the initialized object. but you see this assignment first. So what happened here is that, okay, this is not yet finished, fine, but when T1 enters get instance, it will check, is instance equal none? No. So it will get the instance and work on it. So it will work on uninitialized instance. This is due to relational consistency. The sequential order here is not observed. Maybe because for some reason, these changes are not reflected, or even more, the compiler of Java it's okay for him to change the order of instructions. It's okay. So if he changes the order of instruction, then you are lost. So this example is mistaken. If you do it this way, it's not safe. And this is the price you have to pay for this relaxed consistency. Right. So basically, for working with memory, right. The synchronized blocks themselves are sequentially consistent. So if you have block number 1, and then block number 2, block number 3, it's guaranteed. Executing blocks together, they are sequentially consistent. Right. Modified fields are written to memory on lock exit and memory flushed on entry. Right. So as we've seen the example of the blocks here. Maybe some fields are changed inside your code, inside your block, but there is no guarantee that they are updated back to memory. So they only updated when you exit. What's interesting, if you have volatile keyword fields in your class or your object, they are consecutively consistent. So this means that Java do not cache them into local variables. So every time it updates memory directly. Final fields also are sequentially consistent, but it says here care needed for passing constructs. For passing constructs this pointer before returning. Don't write it correctly here. Final fields are what care needed for passing constructs. Do this maybe. Pointer before returning. Yeah, sure. Maybe let you check it next time. So there's something wrong here with the English actually. Final fields also but care needed for passing constructs. Oh right, passing constructs. Okay, this pointer before return. Okay, so actually what I meant here is that you have object constructs. Sorry. So the thing is, if you are passing a final value field to a construct. So final value takes a constant. You assign it only one value and you can't assign it anymore. So I think what can possibly happen wrongly is that you are still initializing the final field and someone else reading it and you're still initializing. I think this is what's meant here. You can also check it in the book. Anyway, sequential consistency, okay. If you want to implement sequential consistency, of course you can using synchronized blocks and so on. But in Java or high-level languages, sequential consistency sometimes are not enough. Why? Check this code. Okay, imagine that this is the time axis. Right? Right, so imagine that this is the time axis and you have a queue like what we've shown you. Right? So you have this operation, you made in queue x, so you put the x object inside the queue. And then another thread here makes in queue y. And then the first thread will dequeue something. And what it